Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element Californium. What you see here is a macro photograph of the first isolated bulk sample of Californium metal. Calling this a bulk sample may be overstating things a bit. While it is a large sample, it's only 1 millimeter across, and it only weighs 10,000ths of a gram, about the same weight as an average grain of salt. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Californium is the 98th element in the periodic table. Its atomic number is 98 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Like all the elements in this part of the periodic table, we don't have to go back in history very far for the discovery of Californium, only back to post-World War II research performed at the University of California, Berkeley. Californium was co-discovered by this group: Kenneth Street Jr., Stanley Thompson, Glenn Seaborg, and Albert Ghiorso. I really love this photo. You don't often get a picture of all the discoverers together. Seaborg received the Nobel Prize for his work, and an element was named after him, Seaborgium. This was a bit controversial because it was traditional to only name elements posthumously, and Seaborg was still alive. Here he is pointing to his element. Seaborg discovered or co-discovered a total of 10 elements. Albert Ghiorso was involved in the discovery of 12 elements, more elements than anyone else, though he, unfairly in my opinion, never received a Nobel or had an element named after him, although Ghiorsium was proposed for element 118. That name was not adopted and instead named oganesson. I hope Ghiorso is considered in the future. They used the new 60-inch cyclotron built by Ernest Lawrence at the UC Berkeley Radiation Lab, later called the Lawrence Radiation Lab, and even later the Lawrence Berkeley National Lab after the word radiation became too politically sensitive for Berkeley. Since this element was first created at the Berkeley Radiation Lab at the University of California, it was given the name Californium. The previous element, Berkelium, was named for the lab and city itself. In the accelerator, they started with curium-242, which itself had been created much the same way 6 years earlier, but starting with plutonium. See the episode all about curium. The accelerator is used to produce a stream of alpha particles. An alpha particle is a naked helium nucleus consisting of 2 protons and 2 neutrons. When these alphas hit the curium-242, you get californium-245 and an extra neutron. Making californium like this with a cyclotron is a slow, expensive, and not very productive method. Our 4 pioneers only managed to make 700,000 atoms this way. That may sound like a lot, but this would only make a cube of californium 27 nanometers on a side, about 1/4 the size of a single coronavirus particle that causes COVID. It's much more efficient to produce californium in a reactor, though the process is a bit different. We'll talk about that. Here you see the high-flux isotope reactor at the Oak Ridge National Lab in Tennessee, which began operation in 1966. Isotopes produced in the high-flux isotope reactor are separated here in the Radiochemical Engineering Development Center, or REDC. Handling of these dangerous materials is done in a hot cell. Here you see 9 of these hot cells. Scientists are protected by thick layers of lead glass and control the processing with robotic remote manipulators. I'm sure you've seen these in many science fiction films. It's not fiction, though they are sometimes called Waldos, from a 1942 short story by Robert Heinlein in the August 1942 edition of Astounding Science Fiction. Here he was writing under the pen name Anson MacDonald. The only other place you'll find Californium produced is at the Research Institute of Atomic Reactors in Dimitrovgrad, Russia, the equivalent of our Oak Ridge high-flux reactor. Both reactors were designed to produce copious amounts of neutrons useful in the production of many isotopes, not to generate power. We'll need all those neutrons. Let's look at that. In the reactor, we'll start with uranium-238, the most common form of uranium found in nature. Uranium-238 has a half-life of 4.5 billion years, so we don't have to worry about it decaying away during this process. Remember, in a reactor, there are lots of free neutrons available from the fission process. Eventually, our uranium-238 will be struck by a neutron and changed into uranium-239. Uranium-239 has a fairly short half-life of only 23.45 minutes. This shorter half-life is good because the next step depends on its decay by beta particle emission to Neptunium-239, also with a short half-life of 2.356 days, which is good news since we need it to decay by beta particle to our next target, plutonium-239. This first part of our Californium journey is also how they produce plutonium-239 for reactors and weapons. But we've only begun. Our plutonium-239 has a half-life of just over 24,000 years, so like the starter uranium-238, we don't have to worry about it decaying away during the process. Eventually, our plutonium-239 will be struck by 4 neutrons. I won't detail these individual steps, and changed into plutonium-243 with the short half-life of 5 hours. This will decay by beta particle emission to Americium-243 with a longer half-life of 7,350 years. This new element absorbs yet another neutron and becomes Americium-244. Americium-244 has a nice short half-life of 10 hours, which is also good news since we need it to decay by beta particle to our next target, Curium-244, with a half-life of 18.11 years. We're not done, but we're getting there. The Curium-244 then absorbs 5 neutrons, eventually becoming Curium-249 with a half-life of 64.15 minutes. That new isotope of curium decays by beta emission to Berkelium-249 with a half-life of 327 days. Finally, the Berkelium decays by beta to Californium-249. In the reactor, you can keep adding neutrons to also synthesize heavier isotopes of Californium. This was the last element I could find pricing for, and I don't really think it's a very reliable number. You can't look up pricing on Amazon. I found an eye-popping price of $60 billion per kilogram. And of course, that would be a bad investment since it and your money decay away continuously since it's radioactive. Our tiny 1 millimeter sized piece from the beginning of this episode would cost over $600,000, and I think that may be a gross underestimate considering what it took to make that 10 milligram piece. Californium is a member of the actinide series of elements down at the bottom of the table. It's the 10th element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides and their isotopes are radioactive. Let's look at isotopes. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 98 protons for Californium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 20 known isotopes of Californium, and as I mentioned in the previous slide, we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of Californium are radioactive. We don't really find Californium in nature. The word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place. You've used a topographic map to find your place, I assume? All these various isotopes of Californium occupy the same place in the periodic table. Of the isotopes of Californium, these are the longest lived, the ones with half-lives over 1 hour. I'll talk more about half-life in a bit. The longest Californium half-life is Californium-251, with a half-life of only 898 years, and that's why it's not found in nature. All Californium has decayed away. It has to be manufactured, as we've seen. Radioactive elements are unstable and they decay into other daughter products. There are 3 main ways nuclei can decay, and I'm oversimplifying this a bit. First, the nucleus can decay by giving off an alpha particle. As previously mentioned, an alpha particle is simply a helium nucleus stripped of its electrons. It consists of 2 protons and 2 neutrons. Emitting an alpha particle changes the atom to the element 2 spaces previous in the periodic table, since it loses 2 protons. Next is the beta particle. Here, a neutrally charged neutron in the nucleus becomes a proton and an electron. Added together, they still have 0 charge, just like the original neutron. While the proton remains in the nucleus, the negative electron is spit out as a beta particle. Because the nucleus gains a proton in this interaction, the atom becomes the element 1 up in the periodic table. Lastly, and loosely explained, during some decay events, the nucleus can be left in an excited state. When the nucleus rearranges itself to a lower energy state, it can emit a gamma ray, an extremely high energy and penetrating photon. Here, the atom does not transmute into another element. Let's look at the decay series of Californium. We'll start with the longest-lived isotope, Californium-251, with a half-life of 898 years. More on half-life in the next slide. As just illustrated in the previous slide, isotopes can decay in different ways. We'll follow the most likely path, noted here with the bold line, which I'll make bolder and yellow to make it easier to follow. Our first decay is by alpha particle to curium-247. This isotope has a half-life of 15.6 million years. The curium also decays by alpha to plutonium-243, with a half-life of only 4.95 hours. This decays by beta to Americium-243, with a half-life of 7,350 years. Our next step is a decay by alpha particle to Neptunium-239 with a half-life of 2.536 days. I'm running out of room here, so let's push everything up so we can continue. Notice the Neptunium-239 can decay by both alpha or beta, but it almost always decays by beta to plutonium-239 with a half-life of 24,100 years, and remember, we're following the most likely decay path here. Next, the plutonium-239 decays by alpha to uranium-235 with a half-life of 704 million years. We've seen uranium-235 and its decay series before in previous episodes. The rest of this series is called the actinium series, and I won't burden you with the details, but uranium-235 decays through thorium-231, protactinium, actinium, thorium-227, radium, radon, polonium, lead-211, bismuth, thallium, and finally to stable non-radioactive lead-207. If you want a detailed look at the actinium decay series, take a look at the Tales from the Periodic Table episode about uranium. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any radioactive isotope. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait one half-life, one half of your isotope will decay, and we'll have 512 atoms left. If we wait one more half-life, half of that remaining half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice there's one remaining atom after 10 half-lives. If we waited one more half-life, our remaining atom would have a 50-50 chance of decaying in that time. Since we're on our 15th radioactive element, 16th if you include bismuth, I'd like to repeat how radioactivity is measured. There are 3 interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity, the rate particles are emitted. This is probably the simplest thing to measure. You can use a simple Geiger counter and just count the number of detections per second, but you need to take into account the size or area of the detector and its distance from the source, and multiply the measured counts per second as if your detector could completely surround the source and catch all the disintegrations in every direction. The international unit for this is the becquerel, named after Henri Becquerel, who discovered radioactivity. 1 becquerel equals 1 disintegration per second, so most sources are in the kilo, mega, or even gigabecquerel range. In the US, we also use an older unit, the Curie, named after our dynamic duo, Marie and Pierre Curie. 1 Curie is the amount of radiation given off by 1 gram of radium. Radium was discovered by them, get it? 1 Curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Radiation carries energy, and that energy is deposited in your body or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is about the amount of energy used to lift an apple from the floor to a table. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milli or micrograys or something like that. In the US, we have used the unit of the rad, or radiation absorbed dose, which is 1/100th as large as the gray, but still a large amount of radiation. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation, alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to specific kinds of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the US, we also use the rem, which stands for Radiation Equivalent Man. The sievert is just 100 rem, and the rem is 1/100th of a sievert. These are human, health-based units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer, genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts, or 5 rem per year in the workplace. You normally absorb about 67 millirem every year from the environment around you, and that varies depending on where you live. That's 1/75th the allowed annual dose. A dental X-ray exposes you to about half of a millirem. A standard chest X-ray, front and side, exposes you to up to 10 millirem, and a chest CT scan gives you up to an 800 millirem dose. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits should always outweigh the risk. We can talk a bit about a few physical properties of Californium, but there's not a lot really known about this rare element. As you can see, most of the properties have an Na, or not available, next to them. Still, there are a few things we do know about Californium. Californium has a density of 15.1 grams per cubic centimeter. It's a fairly dense element. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds for comparison. You can see Californium's density is significantly higher than lead at 11.34 grams per cubic centimeter, but lower than tungsten at 19.25 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, Californium's density is 15.1 grams per cubic centimeter, near the top of our chart, the 12th densest element, even denser than mercury. Californium has a melting temperature of 1,173 degrees Celsius, or 2,143 degrees Fahrenheit. That's around the 43rd highest melting point, about the middle of our chart, around the melting temperatures of copper and gold. Although this figure is a bit uncertain, Californium boils at 1,743 degrees Celsius, or 3,169 degrees Fahrenheit, giving it around the 59th highest boiling point of all the elements. Below average on this chart. That's only 570 degrees Celsius above its melting point, yielding a fairly small liquid temperature range. One of the subscribers to this channel SillySad 3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of Neptunium, with a 3,356 degrees Celsius liquid temperature range. As I mentioned, Californium's liquid temperature range is far below average, with a 570 degrees Celsius range, the 73rd largest liquid temperature range of the elements. The smallest liquid temperature range belongs to neon, which is liquid in only a 2.51 degrees Celsius range. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. The size of the Californium atom is around 590 picometers in diameter, about 5.6 times the size of the hydrogen atom. Let me quickly mention that the 590 picometer size is not well established and is only a best guess. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are dumbfoundingly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. The size of the Californium atom places it just underneath the size of cesium, right at the top of the chart. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of Californium. It has a moderately simple spectrum with strong reds, greens, and blues. Putting Californium in a flame, don't do that, would make these colors of light. When combined, they would probably look whitish, since adding red, green, and blue light gives you what looks like white light. See my video about color mixing for more on that subject. Spectra of the elements uniquely identifies them to scientists, as each element gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Surprisingly, there are a few real-world applications for Californium, and those depend on its ability to supply lots of neutrons when it decays. Let's take a look at the ways Californium, specifically Californium-252, can decay. 96.1% of the time, Californium-252 will decay by alpha particle emission and become Curium-248. But this isn't the decay mode we're interested in. We're interested in the other 3.01% of the time. Here, the Californium-252 decays by spontaneous fission, where the unstable nucleus splits apart on its own, creating two lighter nuclei and 3 or 4 neutrons. Most of the time 4 neutrons. It's this bumper crop of neutrons that makes it useful. A single microgram of Californium-252 can release up to 170 million neutrons per minute. This extremely high emission rate makes it one of the most intense and compact available neutron sources. In uranium reactors, there aren't enough neutrons from the natural decay of uranium to start up the reactor. You need a source of neutrons to get the fission reactions going. Californium-252 is a good source of neutrons, as we just saw. The Californium is part of startup rods inserted into the reactor core to initiate fission. This is the main use of Californium, but not its only use. To survey what's underground, especially in oil and gas wells, a neutron source, like this one that contains Californium-252, is part of a suite of instruments which may also include a gamma-ray source, something to measure conductivity, and maybe even an ultrasound instrument. These are placed in a package which is then lowered into the well as data is taken. Each instrument gives the geologist a different clue to what surrounds the borehole. The neutron source and detector is useful for determining the porosity of the rock layers, along with water and hydrocarbon content of the surrounding rock. In case you want to look into this further, this is called well logging. In the aerospace industry, neutron radiography is used to inspect aircraft and rocket components for hidden flaws, such as cracks or bad welds. Here, you can see an otherwise invisible defect in what I think is a turbine blade. Neutron radiographs are similar to X-rays, but obviously neutrons are used instead of the electromagnetic X-rays. X-rays are absorbed by dense substances like metals, whereas neutrons are absorbed by lighter atoms, especially hydrogen, and hence give you a completely different picture of what's inside an object. Compare these two radiographs. The top is produced by penetrating neutrons, and the bottom by X-rays. Notice the X-rays completely miss the plastic film cartridge. Plastics are hydrocarbons and have lots of hydrogen atoms, so plastic items show up in neutron radiographs. You can even see the sprocketed 35mm film in the neutron radiograph, but only the thin metal take-up spool in the X-ray. The X-ray photo shows lots of the metal mechanisms: sprockets, film guide rollers, shutter, winding mechanism, and more. The neutron radiograph shows weakly or not at all. You'd think this would be a great diagnostic tool for medicine, but unfortunately, neutron radiography is not typically used on living humans. It would deliver a higher dose of radiation than X-rays and does not easily penetrate our thick bodies. Neutron activation analysis is a powerful tool, allowing you to find out what elements are in a substance. When neutrons hit and are absorbed, nuclei in the rock can transform from a stable isotope to a radioactive isotope. You can then measure the energies of alpha, beta, and gammas given off by these radioactive nuclei, and the energies can tell you which elements and their quantities with good precision. If the half-lives of the radioactive isotopes are short enough, these half-lives can be measured too, adding to the identifying data. For instance, in the U.S., 1964 and older silver coins contained 51.8% silver 107 and 48.2% silver 109, both stable isotopes. After absorbing a neutron, you have radioactive silver 108 with a half-life of 2.42 minutes and silver 110 with a half-life of 24.6 seconds. Both decay by beta into cadmium 108 and 110, respectively. You can measure the betas with a Geiger counter. Gamma rays are also given off and can be measured with a gamma ray spectrometer. Neutron activation analysis is very sensitive, measuring as small as parts per billion. Some additional advantages of neutron activation analysis are you can identify many elements at once, it's non-destructive, and it doesn't require sample preparation. Neutron activation analysis is used in forensics, archaeology, environmental science, material science, and other areas. One last use of Californium is as a target material to make other super heavy elements in the periodic table. Heavier actinides like fermium, mendelevium, etc. have isotopes with very short half-lives or are unavailable in the required amounts. So Californium is about as heavy as you can practically use for a target when attempting to reach the highest elements. Researchers electroplate and mount milligram-scale amounts of californium onto thin backings and bombard them with accelerated projectiles, most commonly calcium-48. Here, The Californium-249 target is hit with a calcium-48 nucleus, producing the highest element we know of, oganesson-294, and a few neutrons. Here's the whole reaction written out for you chemists. The OG star is the intermediate excited oganesson, which then ejects the 3 neutrons. The oganesson-294 has a half-life of only 1/2 of a millisecond and decays by alpha to livermorium-290. Californium serves no known biological purpose, and you hopefully have none of this stuff inside you. As usual, we'll end this talk with Mary Soonley's elemental haiku about Californium. Freely fissioning, spitting out enough neutrons to start reactors. In the next program in this series, I'll examine the element Einsteinium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about Californium. For more Tales from the Periodic Table, see this playlist on my YouTube channel. And of course, I'm required by law to say this, smash that subscribe button.